So in this part, we will study the last two series tests that we will consider in this course. We have the ratio test and the root test. Okay? These two tests, their conclusions are very much similar. Okay? So later, we will see that whatever conclusion ratio test will give, it will be also the same conclusion that the root test will give. Okay? So first, let us recall some tests that we have discussed. The alternating series test. So you have the alternating series. And suppose you have here the Bn satisfies these two conditions here. Okay? Of course, in here we are assuming, in here and in here we are assuming that Bn, they are positive for all n. Okay? So if these two conditions are satisfied, then the series is convergent. Next, absolutely convergent series test. You have a series. If it is absolutely convergent, then the series is convergent. Okay? And again, you can have a series which is convergent but not absolutely. That means that the series is conditionally convergent. Okay? Now, the alternating series test and the absolutely convergent series test, you can consider even non-negative integers or non-negative terms. Unlike in your comparison test, integral test, and limit comparison test, you have to have terms which are all positive. Or you can have all negative, but you need to modify. You need to factor out the negative so that you will only study the series with positive terms. Okay? For the alternating series, you can have negative terms. But this is very specific. You need alternating in signs. Okay? Absolute convergence series test, the absolute convergence test, you can have either all positive, all negative, alternating terms, or even not alternating terms. You can use any general series there. Okay? For the next two tests that we are going to discuss, you can use that with any series, just like the absolute convergence test. So let's start with the ratio test. Suppose you have the series an from 1 up to plus infinity. And suppose this series has non-zero terms. Take note of that, non-zero terms. So it could be alternating as long as the terms are not zero. Could be all positive, could be all negative, and it could be any behavior of sign change. So any general series. We consider the ratio a sub n plus 1 over a sub n. We get the absolute value of that. And we find the limit. Let L be the limit of that ratio. If the limit is less than 1, okay? If the limit is less than 1, then the series is absolutely convergent. And it means the series is convergent. Okay? If the limit is greater than 1, or the limit of the ratio is plus infinity, then the series is divergent. Okay? So again, you compute for the limit of the ratio a sub n plus 1 over a sub n. You get the absolute value first. You have the limit L. If L is less than 1, the series is absolutely convergent. If L is greater than 1 or L is plus infinity, the series is divergent. Now notice there's no equality to 1. Okay? The equality to 1, it will give you inconclusive result. Meaning you cannot conclude whether the series is convergent or divergent. You need to use another test. Okay? Okay? Example. Determine whether the series n to the n over n factorial converges. Solution. So your a sub n here, this is n to the n over n factorial. Okay? So you want to find the limit as n approaches plus infinity of the absolute value of a sub n plus 1 over a sub n. Okay? So this is just the limit as n approaches plus infinity. You have here n plus 1 raised to n plus 1 divided by n plus 1 factorial. And then here, a sub n, it's a denominator. So we can do the multiplication, but we need to get the reciprocal. This is n plus 1 over n to the n. And these are all positive. So we can remove the absolute values. And then let us just rearrange. Let's rearrange the expressions. So limit as n approaches infinity. Here you have n plus 1 raised to n plus 1 divided by n to the n times n factorial over n plus 1 factorial. And then we further manipulate the expression. Limit as n approaches plus infinity. We will have n plus 1 times n plus 1 to the n coming from here. And then, of course, you just have n to the n here times. You have n factorial. And then, on the denominator, you can rewrite it as n plus 1 times n factorial. So recall your n factorial, this is n times n minus 1 times n minus 2, etc. times 2 times 1. But this is also n times n minus 1 factorial. So if you move to n plus 1 factorial, this will become n plus 1, this will become n plus 1, but you will have n plus 1 minus 1, so you have n factorial. You will end up with this. And as you can see, this guy here will cancel this. This guy here will cancel this. And then these two guys, you can combine them into a single power. This guy here, this is equal to the limit as n approaches plus infinity of n plus 1 over n raised to n. This is equal to the limit as n approaches plus infinity of 1 plus 1 over n to the n. Okay? Question so far? Now look, this guy here, the limit, it's equal to E. Okay, let me write it here. The limit of that, it's equal to E, which is approximately 2.718. And this is greater than 1. Okay, that's greater than 1. Okay, therefore, by the ratio test, by ratio test, the series n to the n over n factorial, and from 1 up to plus infinity, this is divergent. Okay? Okay, so here we just showed ratio by ratio test that this series is divergent. Let's have another here. Determine whether the series converges or diverges. So in here, you have an alternating series because this guy here, this is -1 to the n minus 1. These are all positive. So this is an alternating series. You can use your alternating series test in here. Okay? So you can use your alternating series test. So solution 1, one can use alternating series test. But we will do the ratio test instead. So in here, you have your an to be -1 raised to n minus 1 n squared over 2 to the n. Okay? And then we'll have to find the limit a sub n plus 1 over a sub n, absolute value. We let n approach plus infinity. And then we can remove the -1 to raise to something, because it's always -1 or +1, but we have absolute value. So they'll just become +1. So in here, we'll just have limit as n approaches plus infinity. And then a sub n plus 1, you have n plus 1 quantity squared over 2 to the n plus 1 times a sub n on the denominator. So we do multiplication, we get the reciprocal. So this is just 2 to the n over n squared. And then we just simplify this. Again, we'll combine the same or similar terms. We have n plus 1 squared. We put on the denominator the n squared. And then on the other side, you have 2 to the n. You have 2 to the n plus 1. You can write it as 2 to the n times 2. And therefore, you can cancel these two guys here. So 2 to the n cancels with 2 to the n in here. And then you will have 1 over 2 there. Let me write it here. You will have the limit n approaches plus infinity. You have 1 over 2 there coming from this. And then you can combine this into a single power again. So you will have n plus 1 over n quantity squared And as n approaches plus infinity, this guy here, this is just 1 because you're just squaring it. So this is equal to 1/2. And this is less than 1. So by ratio test, the series -1 to the n minus 1 and squared over 2 to the n, and from 1 up to plus infinity, this is absolutely convergent, absolutely convergent, and hence convergent, and hence convergent. Okay? Now, this ratio test, so this ratio test, it's always helpful if you have, say, factorials. Also, say, powers. Okay? Like this. Okay? You have this or this guy here. Ratio test is really helpful. So if you look at this, you have power 2 to the n. Here you just have a polynomial, it's totally fine. Okay? So those are some hints, okay, that will let you think that ratio test is the one you're going to use. Now let's talk about the other test, root test. So suppose we have the series a sub n, sum a sub n, and from 1 up to plus infinity. We let L to be this guy. So you get the absolute value of an, you raise it to 1 over n. This guy, it's also written this way. Absolute value of an, you get the nth root of that. And that's why this is called root test, because you get the nth root. Okay? Now, if L is less than 1, if L is less than 1, the series is absolutely convergent. And again, therefore, convergent. If L is greater than 1, or the limit is plus infinity, then the series is divergent. So you see now, it's really similar to the ratio test. Okay? And just like the ratio test, it will be inconclusive if the limit is equal to 1. In this case, you use another test. But don't try to use ratio test because you will get the same conclusion, meaning the limit will still be equal to 1. So you have to use another test. Okay? Let's have this. Determine whether this series here converges or diverges. Now, a hint, if your terms, if all the expressions in the terms have exponent n, just like this, you have n to the n, here you have e raised to 3n. Root test is very helpful. Okay? Why? Let us see. So in here, an, this is equal to n to the n over e to the 3n. So you want to compute for the limit as n approaches infinity, absolute value of an or a sub n. You raise this to 1 over n. So this is equal to the limit as n approaches plus infinity. Let's remove the absolute value thing because these are all positive. So you'll just have n to the n over e to the 3n. You raise this to 1 over n. And what will happen? N to the n raised to 1 over n, that's just n. And then on the denominator, e to the 3n raised to 1 over n, that's just e to the 3. So as n approaches plus infinity, this is equal to plus infinity. So by root test, the series n to the n over e to the 3n, and from 1 up to plus infinity, this is divergent. Okay? Questions? Let's have another here. So test the series. Sum negative 2 to the n over tangent inverse n raised to n, and from 1 up to plus infinity for convergence. So in here you have a sub n. This is negative 2 to the n over arctan of n raised to power n. So we want to find the limit as n approaches plus infinity. So notice this guy here has power n, this guy here has power n. Root test will be helpful. So limit as n approaches plus infinity, absolute value of a sub n over raised to 1 over n. So in here you will have the limit as n approaches plus infinity, absolute value of negative 2 to the n over arctan of n raised to n all over everything raised to 1 over n. The absolute value here, it will remove the negative here. Okay? So again, the absolute value here, it will remove the negative here. Now you have power n here. You have 1 over n here. Here you have power n, 1 over n here. So we have limit as n approaches plus infinity. Numerator, it's just 2. Denominator, it's arctan of n. So as n approaches infinity, arctan, sorry, this is just negative 1 here. So again, as n approaches plus infinity, arctan of n will go to pi over 2. So this will be equal to 2 over pi over 2, or this is equal to 4 over pi. Pi, it's less than 4. It's approximately 3.1415, etc. It is less than 4. So 4 over something less than 4, this will be greater than 1. So by root test, right, the series is divergent. So the series negative 2 to the n over arctan of n to the power n, and from 1 up to plus infinity, this is divergent. Okay? Questions? Next, determine whether the series negative 2 to the n over n to the n converges or diverges. So again, you have this expression, it has power n. This expression, it also has power n, so we can use root test. So in here, you have a sub n. This is negative 2 to the n over n to the n. Okay? Or simply, you can write this as 2, negative 2 over n to the power n. They are the same. You can actually do this to the previous examples. But now we have the limit as n approaches plus infinity, absolute value of a sub n raised to 1 over n is the limit as n approaches plus infinity, absolute value of negative 2 to the n raised to n, everything raised to 1 over n. So just like before, the negative will disappear because of the absolute value, but this will just become the limit as n approaches plus infinity of 2 over n. So as n approaches plus infinity, this will be 0, and this is less than 1. So by root test, the series sum negative 2 to the n over n to the n, and from 1 up to plus infinity, this one is absolutely convergent. And hence convergent. And hence convergent. Okay? Questions? Next, for which values of x does the series x minus 2 raised to n over 9 to the n from 1 up to plus infinity converge? Okay? So, this is a series. This guy here, it is a series, but with the variable x. Okay? This series we will discuss in more details on our next meeting. There is a name for this type of series where there is a variable. Okay? So we will discuss that further in our next topics. But we can answer this. For which values of x does this series converge? So we want to find those x's that will make this series convergent. Okay? This is how we're going to do it. We will actually use ratio test or root test. But most of the time, for this type of questions, okay, we will use ratio test. So how do we do this? So you have your a sub n. This is x minus 2 raised to n over 9 to the n. Now, we want the limit of a sub n plus 1 over a sub n. You have to get the absolute value of that ratio. Okay? So let us compute for this. Limit as n approaches plus infinity. So you will have absolute value x minus 2 raised to n plus 1 over 9 to the n plus 1 times you will have here 9 to the n over x minus 2 to the n. And then just like before, we combine this guy here and this guy here into a single fraction. Also, this guys here. So we will have the limit as n approaches plus infinity. We still have that absolute value. The reason is you have a variable x. Okay? And then you will have x minus 2 to the n times x minus 2. That's your x minus 2 to the n plus 1. On the denominator for this, you have x minus 2 to the n. Times, you have 9 to the n over 9 to the n times 9. That's your 9 to the n plus 1 on the denominator there. So notice, this will cancel this. This guy will cancel this guy. So you will have limit as n approaches plus infinity of absolute value of x minus 2 over 9. But notice, this guy here doesn't have any n, which means this is the limit. So this guy here is the limit, absolute value of x minus 2 over 9. Take note, 9, it's always positive, so we can remove the absolute value for that part. On the other hand, x minus 2, it has a variable x, so you will have possibly negatives. In fact, if x equals 0, you have negative 2. So you have to put the absolute values. Okay? What now? You have this limit. You want this series to be convergent. So you want this limit here to be less than 1. Correct? If this guy here, it's less than 1, then the limit will be less than 1. And according to the ratio test, if you have the limit less than 1, therefore, the series is convergent. Actually, absolutely convergent. Take note, it should be strictly less than 1. Okay? But anyway, this means that you need your x to satisfy absolute value of x minus 2 over 9 less than 1. This means absolute value of x minus 2. This must be less than 9. Again, you need absolute value of x minus 2 over 9 to be less than 1. This means that absolute value of x minus 2 must be less than 9. And then we use this property of inequalities. Absolute value of x less than a. This is minus a less than x less than a. So using this property, this means we will have minus 9 less than x minus 2 less than positive 9. Or that, you add 2 on all parts, you will have minus 7 less than x less than 11. So this means if x is inside the interval negative 7, 11, then the series x minus 2 to the n over 9 to the n and from 1 up to plus infinity is absolutely convergent and hence convergent and hence convergent. Okay? But this is the case when the limit is less than 1. Okay? And like I mentioned earlier, if the limit of this guy here is equal to 1, then it will be inconclusive. The series, we don't know if it is convergent or divergent. Okay? Now, if this is equal to 1, it means you need to use x equals negative 7 or x equals 11. Okay? So if limit absolute value a sub n plus 1 over an as n approaches plus infinity, this is absolute value of x minus 2 over 9. If this is equal to 1, okay, then your x must be equal to negative 7 or x equals 11. That's just based on this computation. Okay? That's just based on this computation. As well as this, you just put everything equality. Okay? It's just, or they are just the endpoints of your interval. So we will talk about that later. But you will be able to see that if the limit is equal to 1, then you will have these two guys for x. But why are they important? Because there's a possibility that they are convergent or divergent at those points. And we are asked to determine for which values of x the series converge. So we have to check these endpoints. Look, if x equals negative 7, then you will have the series n equals 1 up to plus infinity, negative 7 minus 2 to the n over 9 to the n. This is equal to what? Sum negative 9 to the n over 9 to the n, and from 1 up to plus infinity. This is just the sum negative 1 to the n, and from 1 up to plus infinity. This is divergent. Which is divergent here? So which is divergent? Okay. If x equals 11, then the series 11 minus 2 to the n over 9 to the n, and from 1 up to plus infinity. This is just the sum 9 to the n over 9 to the n, and from 1 up to plus infinity, this is just the sum of 1, and from 1 up to plus infinity, this is divergent, which is also divergent. Okay? So, therefore, the series x minus 2 to the n over 9 to the n, and from 1 up to plus infinity, only converge for x inside the open interval negative 7 up to 11. So this is the answer to the problem.